What I want to look at in this video is defining the equation of a line in three-dimensional space. Now, up to National 5 and higher level mathematics, we looked at lines in 2D, so y equals mx plus c. But now that we're looking at planes in three-dimensional space, we've got that third direction coming into play. So we've got that third dimension coming in, which is our z dimension. So we have to start taking that into account now. So we have to start looking at how we can define a line in this three-dimensional system such that we're able to use it in some of our calculations relating lines to planes. Now, when it comes to calculating the equation of a line, there's two key bits of information that we need to know every single time in order to be able to do that. Now, those two key bits of information are firstly the direction the line runs, and then secondly a point somewhere on that line. Now let's imagine, I'm going to show you how this would work. I've got a point A. Now that point A, I'm going to tell you its coordinate is x1, y1, z1. What I'm also then going to do is define a line L which goes through that point A. Now somewhere along that line, what I'm also going to do is define a point P. Now this point P sits on the line at a coordinate x, y, and z. Now what this point here is going to be used to define is any generic point upon the line. So what I'm able to do is determine some sort of equation where I've got P equals, and that can then tell me every single coordinate upon the line on that system. So what I'm going to do is, as well as having this, what I'm going to do is take an O here and let that define the position vectors A and P within my system. Now, because this is a line, A to P has some sort of direction. What I'm going to do is define a direction vector U which points in the same direction as that vector. What that then means is the distance between A to P is some multiple of that vector. So what that means is it's T times U. So it's going in the same direction, it's just a different magnitude to that direction vector U that we've defined. What this then means is I can say my vector A to P is given by this T times U. Now, using the definition of how we calculate this vector, using the positions vectors for P and A, what I can say is that P minus A is equal to T times U. So P is equal to A plus TU. So what that means is this is the line upon my system, so the point that we know, and this U is the direction that we know the line goes in. Now what we can do is take each of the bits we've defined here and plug them in, so we've got a component form, and what that means is I'm going to have P equals XYZ in component form, which because of this relationship is going to equal x1, y1, z1, and then that's going to be plus t, and what I'm going to do is define my vector ABC as being my direction vector u. So I'm going to say that u is equal to A, B, C there. So what that then allows me to do is have the component form of this equation of a straight line. Now what I'm able to do at this point is multiply this bracket here and gather like components. So what I'm then able to say is that I've got XYZ equals x1 plus TA, y1 plus TB, z1 plus TC. What that then lets me do is write each of these out and say fine, so I know then that x equals x1 plus TA, y equals y1 plus TA, and z equals z1 plus TA. Now this here is what's called the parametric form. This is called the parametric form of our line. And t within this is our parameter. So that there is the parameter. within our system. Every different value of t will give a different set of coordinates x, y and z that we can use anywhere upon our line. What we're also able to do is take each of these and rearrange them such that we get t equals for each component. So for example, the x1, what I could rearrange it to get is that t equals x minus x1 over a. I could do the same for the y and the same for the z. What that then lets me do is write down a new relationship where I can say fine, so what that means is x minus x1 over a equals y minus y1 over b equals z minus z1 over c. And all of those are the equivalent of t. Now this here, this is called the symmetric form. So that's the symmetric form of our line in three-dimensional space. This also, you can see it written as what's called standard or canonical form within textbooks somewhere. But we're going to tend to stick to the name symmetric form. Now within this, you'll notice that the x1, y1, z1, they all come from the point A, and the ABC all come from the vector which is in the direction of our AP. So we've got three different ways of defining it. We've got this first one here, which we know is the vector equation. I'll actually note that down this time as well. So that's our vector equation. We've got our second one here, which was the parametric form of our equation. And we've got the third one here, which is our symmetric form. All three of them are interchangeable and we can work our way through each type. Some questions will ask you for a set format, others will leave it open to interpretation or may even ask you to do all three formats. What you need to know is how to define each of them, the difference in the way that you write each of them, and how we can use each of them when we're doing calculations within our textbooks. Now, there's a couple of things that you need to remember and note about the symmetric form of a straight line. There's a few key things that may come up in relation to this. Now the first thing being, at the end of that we had equals t. Now that's often omitted, but needs to be placed back in to convert between the different forms of the equation. So quite a lot of times you'll just see them write x minus x1 over a equals y minus y1 over b equals z minus z1 over c. Quite a lot of the time they won't put the equals t at the end. However, when you're converting it back, that equals t has to be put in for each of the components. So you'd have to write x minus x1 over a equals t, y minus y1 over a b equals t, and z minus z1 over c equals t to convert between the types. Second one is that if any component of the direction vector is 0, then some elements of the symmetric form will be undefined, so the parametric form may be a better variation to use compared to this. Because if you think about it, if the direction vector has any part 0, there's going to be an a, a b or a c equal to 0 in those, which means we'll be dividing by 0, which we didn't like in mathematics. We don't want to break maths, we can't divide by 0. Next one is that each point on the line L is uniquely associated with the value of the parameter t. So every single point on that line is uniquely associated with a value of t, so every single value for t I pick will give me a different point upon the line. Every single point depends upon that parameter t. And the equations of a particular line are not unique, so it depends really on what point you're given upon the line. If I give you 1 point, you might get a slightly different variation from if I give you a different point upon the line. Alright, so as long as your calculations beyond that hold consistently, you may have a slightly different variation on the answers in the textbook, but it should still be valid as long as you've done the correct calculations. So let me show you an example of what I mean by this and how to use it. So let's imagine I've got a point 1, negative 2, 8, and I'm telling you that there's a line which passes through that point and it's parallel to the vector 3i plus 5j plus 11k. I'm then going to ask you, does this point lie somewhere on the line? So what we're able to do is we have a direction and we have a point upon the line. So what we're able to say is that our point upon the line, the position vector of our point along the line, which was A, is given by 1, negative 2, 8. And the position vector of our direction, which was u, is going to be given by 3, 5, 11. So what we're able to do is just directly substitute in. Now remember, for symmetric form, it was x minus x1 over a equals y minus y1 over b equals z minus z1 over c. Now I'm going to keep the equals t in here because it will come in useful later. If you didn't put the equals t, that's fine. As I've said, you may not see it written in some textbooks and some exercises that you'll do. And then all I need to do from this is directly substitute into that equation in order to be able to get my solution. Now remember this point here, that's your x1, y1, z1. And the direction vector, that's your a, b, c. So all I can do is I can simply say fine. So I know then that x minus 1 over 3 equals y. Now it's minus minus 2, so it'll be y plus 2 over b equals z minus 8 over 11. Sorry, this b should be a 5. And that equals t. So what I now want to do is ask myself the question, does that point, negative 2, negative 7, negative 3, lie upon that line? Well, what we need to do is take each element of this and break it down and substitute in the corresponding part of these points. If I do that and I get the same value for t each time, it lies on the line. So if I was to look at the x part and substitute in the x part of this point here, I'd get negative 2 minus 1 over 3, which is negative 3 over 3, which is negative 1. If I looked at the y component, I'd get negative 7 plus 2 over 5. So that's negative 5 over 5. That's negative 1. And if I looked at the z, what I'd end up getting is negative 3 minus 8 over 11. So that's negative 11 over 11. So that's negative 1. So it's held consistently between all three of them. All three of them give me the same value of t equals 0. So therefore I can say that the point negative 2, negative 7, negative 3 is on the line. If I got any of these values not equal to each other, even if it was only one, so say my x and my y were both correct with negative 1, but my z was negative 2, that point still would not lie on the line. The parameter t is not satisfied for every single part of that unique point on the line, so it can't be given by that value t, therefore it does not lie upon the line. So bear that in mind when you're working with it. This parameter t is vital to these calculations. It has to satisfy everything relating to that point. We can't do anything without it being the same, so we have to match it up. Working with the three different formats of the equation of a line is not difficult. We have to be able to interchange between them and we have to be able to apply it to questions. But beyond that, it's actually fairly straightforward to work with, and we shouldn't have too many issues as long as we remember all the rules, the information we need, and how to work with vectors in three-dimensional space so we can relate it back to this sort of scenario.